Oh, that would bother me. Seriously, you can leave it there. Oh, there you are.
You got, sorry, I just didn't realize.
You use the.
Oh, you want the lab? Gotcha.
Oh yeah. And then I need the regular make.
Copy.
Oh, here it is. Yeah. This is for today, right? These notes? No, that was in the banquet. Oh, okay. Last night. Oh, I was here. Yeah, that was last night. Okay, cool. I was thinking about where my place is. Cool. Yep. Yeah, thanks for having me.
Right on. Yeah, that's a pleasure.
Yep. I see the like. How to pronounce the acronym? Oh, there it's.
That's the way it's just perfect. Maybe just essentially have the T in there.
Yeah.
Maybe throw the N if you like, and then at the end of the S, I've got this. So the M's in the middle. All right.
Yes. Whatever. It's not what this doesn't.
I don't think they are. I don't think.
I say it AMP after this. That's the only way I can get it. Yeah. Certainly. My son said language.
Check 1 2.
Say it like see. I said you're right. That's the way big balance.
Check 1 2. Check 1 2.
Well, there was this.
Yeah, so you're doing the intro.
I will. In a second. Just make it set up. I got the.
Check 1 2. Check 1 2. Check 1 2.
I got the.
That's good. Check 1 2. Check 1 2. Check 1 2. Check 1 2. See Danielle.
Okay.
Check 1 2. 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 Check.
Yep. He just went outside.
Okay. Well, bit. Sure.
There he is.
It is on, and this here's the meat. When you get comfortable with it, when you enter the test.
Audible here. Oh, yeah, okay, good. All right. That sends the test.
I'm not sure because you go back into that role.
Okay.
Ellen was coordinator reps. After I'm done with CPM, I'm going to stay on the board, but when I do that. Great conference. What did that do?
For the, what does that driving for Gary?
It's mostly like let me get the one out. The opposite of doing that is very massive. Actually, with your recovery of like weekend and year. You like one to kind of like specific about
My favorite color.
Check this slide here.
She should be down.
That's not let me ask you.
I think it's sorry.
Sorry.
Yeah, that's right.
Whatever. Yeah. Good morning. Welcome to day 2 of our fall conference. It is my pleasure to introduce our Saturday keynote speaker. Our speaker is known to many as the Math with Bad Drawings guy who loves math and cannot draw. He has written 4 books. His 2018 book, Math with Bad Drawings, has sold more than 100,000 copies worldwide. That's impressive. His other books include Change is the Only Constant, Math Games with Bad Drawings, and his most recent book, Math for English Majors. His work has appeared in The Atlantic, Popular Science, the Los Angeles Times, Vox, and many other publications. He has taught middle school, high school, and college math. Even as his writing career has taken off, he has prioritized remaining in the classroom and spending his days with students, who are frankly much more interesting than Word documents. He currently lives in St. Paul, Minnesota with his wife, their 2 daughters, and his inordinate fondness for sweets. Please help me welcome Ben Orlin. Just like
Thanks everybody for being here. Am I audible? Oh, okay, but not deafeningly audible, like a good amount of audible. Thank you.
Yes.
Thanks. Oh, beautiful. Yeah, thanks so much, Dan, for the introduction and for inviting me, and thanks everyone for being here. I haven't been here, right? As Dan mentioned, I live in Minnesota now, but I grew up in Boston, so I'm East Coast by nature. And Minnesota's great. People there are very nice, very friendly, very like accommodating and polite. It's terrible. It's exhausting. So I thought my first conversation I have here, I just introduced myself to someone, and it's where we're coming from. So from Minnesota, I'm giving the keynote on Saturday, and so my new friend Rebecca, she was like, "Why are you giving the keynote?" Which so that was a good welcome to New York. I appreciated that. That's all. Yeah, this is where I belong. I want those kind of questions. So these slides, I think she actually couldn't make it this morning, but these first slides are for her. So I just wanted to show real quick see if my slide advance is working. Okay. So for my first book, just real quick, why am I giving the keynote? I do books now. I started out, the way I like to explain it is I started out as a full-time teacher doing kind of weird math writing cartoons on the side as a passion project. And then in a switch I still can't really explain, somehow that became my full-time gig, doing weird math cartoons, and now teaching is what I do on the side as a passion project. It's anyway, very, very lucky and strange life. Anyway, my first book was Math with Bad Drawings, and kind of all like what we coldly call applications of mathematics, but what you might call, I don't know, places that mathematics works magic in the world. So one example, a chapter I did was the fact that you get siblings who look very, very similar, almost like twins, and siblings who look almost like strangers. And that's kind of weird, but it's just exactly what the binomial theorem would predict. So anyway, that was a chapter I did. The second book I did was Change is the Only Constant. It's about calculus, kind of a calculus storybook. Probably my favorite chapter in there is the one about Elvis, the dog who knew calculus. Just a wonderful soul who graced this planet for 13 years and ran along the beach, and in doing so solved calculus problems. I did a book of pencil and paper games. This came out 2022, so a couple years ago. And that was fun, just like games you can play on a grid or with a piece of paper, maybe a die or something. It's just kind of simple, fun games with some latent math. The math is there, but not so overt in most of these games. And then the newest book, which came out just a couple months ago, is about how do I put it? It's kind of my back to basics book. It's sort of all the stuff I was steering clear of in the other books, the things that we need to teach as teachers, the stuff you do in school. But if you just want to get people excited about math, you talk about genetics and you talk about dogs and you talk about games and you kind of don't really talk about algebra. I was like, oh, let's go back and get that stuff. So stuff like negative numbers, why do they work the way they do? And what's the basic message being communicated by negative numbers? They're relevant to my current life in Minnesota. So anyway, but what I want to talk to you about today, and I'll try to have you guys talk a little bit too, because I think there's only so much of the sage on the stage that makes sense. Is a question that this was put to me by my boss. I was my second teaching gig 10 years ago. So teaching was a lovely job. I was teaching in the UK. I lived there for 3 years. And this like lovely school founded 1552, school so kind of old and classic that there was no Shakespeare on the curriculum when the school started, not just because the instruction was in Latin, but because Shakespeare was going to be born like 20 years later. So it was sort of like depth of academic history that like in the US almost doesn't compute. Like we didn't have the US back then. There was a photo I took out the back door one morning. So really, compared to the first job I had, which was in a former used car dealership in Oakland, California, this was a nice setting. Anyway, so one morning, my boss, who's a great guy, Neil, comes up and he asks me, as I remember it, there was almost no more introduction than this. He just comes and goes, Ben, I was thinking, does each person have a mathematical ceiling, a level beyond which they'll never be able to advance? And then he walks away. So what was that, Neil? You can't just come drop a bomb like that. I later found out he was sort of aware of my blog. That's how my writing career was getting going. I had a blog that was building some traffic and building some attention. And he just wanted to see if he could puppet master me. Just walk up and drop a question, and then suddenly that would become a blog post or become a chapter in a book. So it turns out he's a very effective puppet master, because here I am 10 years later and on a different continent talking about that question. So it's a question that I think comes up a lot if you talk to not math teachers. Right? So you talk to people out there in the world, the way they characterize math education is kind of something like this. You are moving through the grades, and you're moving through these symbols, which stand for something. And it goes from numbers, maybe in weird formations like fractions, and then you get into these algebraic symbols, and a lot of people will say, that is where math lost me. Letters. Damn letters in math class. There's something about that. So it's almost a universal thing I hear. And then eventually you get into your undergraduate degree and, you're doing, limit definition of continuity. And the idea is that at some point, I think a lot of people have this experience. At some point, you hit your limit, right? So maybe it's there with fractions and you look at it and you're like, I don't know what that's talking about. Or maybe it's with algebra, or very possibly, probably for many of us in this room, it's with analysis. And what's weird about it is even though a fifth grader is 10, a fifth grader is a kid, when you're in your third year of college, you're functionally an adult. But somehow the experience is very similar. that you hit this level that just isn't clicking for you, and your mind kind of goes blank, and you see skulls, and you get this taste of your own mortality, and that's it. That's kind of the end of your mathematical experience. Like, okay, you've lost the game now. No more lives, no more ability to continue. You can start from the beginning, or that's it. You've been kind of flushed out of the system. And so I think that's how a lot of students experience. I think that's what happens to a lot of people, at least as they would tell the story. So I was on Twitter at the time, so I went on Twitter and I asked the people who followed me on Twitter, a few thousand people, because we're ordinary people, these were math teachers. So not necessarily a representative sample, but I asked them, okay, like, what do you think of this question that Neil had given me? And of course they said, oh, no, there's no ceiling. No way. Right? So some of the answers were, as long as we believe new research about neuroplasticity, there isn't a knowledge ceiling, only an effort and a teaching ceiling. Definitely not. Just take some, or a little or a lot longer. Desire to learn is essential. I think the only ceiling is in the learner's evaluation of their own ability to do things. No, because I reject the idea. This one I like. I reject the idea that even with time and persistence, there are things I couldn't learn. It's like, no, I reject that entire theory of learning because I want to be able to do analysis. And that would say maybe I can't. And no, I'm capable of anything. I mean, this is odd. Like, so this is probably similar to the answer I gave Neil in the moment. But then I got one other response from a woman named Karen, who I've corresponded with a little bit. And she is, how to put it, the kind of person who I think as a teacher, I wish every person were like this. And in practice, it's like 1 out of every 10,000. She's someone who during adulthood, she was like, you know what? I'd like to learn more math. It's like in her 50s and 60s, she was taking online courses, doing some MOOCs. She was reading books. Like, I hadn't written my book yet, but eventually she'd read my books and books like that, Keith Devlin's books. And then she was like doing on message boards, like just trying to learn math. Which, like, our students do it because they're required by law, right? Like, we have set up a system where it is mandatory to learn math. Karen was just doing it for the love of the game. She was just doing it out of curiosity. And this is what she said. She said, is there a ceiling? Yes, 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 yes. And for some of us, the ceiling is pretty low. The teachers all say no. Like, she's heard our messages. She's heard what we say about it. But this superannuated student with abundant grit, desire, effort, and work and approaches, I've got all the stuff we're supposed to have. I just disagree. You can feel the ceiling, she says. I'm hitting it. And so this, for me, is, I don't want to say the essential tension, but one of the essential tensions of teaching mathematics, which is I didn't get into the game because I wanted to tell people where their ceiling was, right? Like, you get into teaching because you want to expand people's horizons and their sense of possibility and what they can do, not because you want to be like, oh, yep, you've maxed out. You're out of the tournament. See ya. We're down. No, I've winnowed you. You're sorry. You're going to have to pack your knives and go home, leave the island. That's it. You've been eliminated. Like, that's not why we teach. But also, you don't get into teaching to like deny students experience. To be like, no. Your narration of your experience, that's wrong. Sorry, incorrect. So like, how do we simultaneously take seriously what the students feel, which is like, no, that's my limit in math. I can't do this. With what we believe and know through experience, which is people can do incredible things. The human brain is an extraordinary instrument, and I don't base that on research that I've read. I base that on having seen how people live and learn. So how do we reconcile those? And my kind of weird answer is what I call the parable of the broken futon. So this goes back to freshman year of college, so before I was a math teacher. Let's see, we had no futon in my room. We lived on the 4th floor. There were some guys on the 1st floor who were getting rid of a futon. So, okay, this is great. So they carried it up for us. And on the way up the stairs, when they arrived, they're like, oh, here's the futon. The metal part fell off. And we were like, oh, where did it go? And they were like, I don't know. Probably on the futon. I'm like, okay. So we couldn't tell where it was. You said the futon was fine, right? The futon worked okay. Like, you could sit there, you could watch TV. It felt like a futon. So that was fine. And then a couple days later, it was like kind of developing a noticeable U shape, a little bit of a valley. Still okay. And then like maybe 2-3 weeks later, it was like a 1-person futon now. And then within a month or two, it was like, no, that was it. The futon collapsed. It was now like a gnarled heap of metal with just a futon mattress kind of draped over it, trying to disguise the wreckage beneath. So it didn't take long. It went from like a futon that seemed totally functional to a wreck. Because there was this little metal piece and we couldn't even figure out where it belonged. But that little metal bar, I guess that was kind of important. So to rewind a few slides, what's the experience of math education? Things are going fine. I can solve these problems. I can do this worksheet, 10 out of 10. And then maybe a few weeks later, there's a test, and you're like, oh, I didn't get 10 out of 10. That's fine. I got 85. I got 90. Like, there's that one question. I don't know the answer. And honestly, I don't even really understand the explanation. I guess I know the answer is 7, but that's fine. Like, I got most of it. And then the next year, it's like, I don't know if I'm following this. This is a little weird. And then you get to the next year, and maybe it's calculus, or maybe it's algebra, or maybe it's fractions. And the futon collapses. You're like, I'm lost. I don't know what's going on. My mathematical understanding is a heap of metal, and I'm trying to throw a mattress over it to disguise it, like a sheet over a cadaver, but there's nothing living under there. And so that's, I think, what happens. That's my image for the experience that students are having. There's some missing piece. And so anyway, I've been talking for a few minutes now. Will you take a minute, turn to someone next to you, someone you brought with you, a safe known buddy or a dangerous stranger. Don't worry, New Yorkers, I'll warn you, New Yorkers very a direct people, a frank people, an honest people, but a loving and decent people. So you can have faith that whoever's next to you will engage with you in good faith. Take a minute. So there's things in any class we teach that are just like tough because that's the new stuff. There's also things in classes we teach that are tough because that's the thing that I kind of wanted you to know already, right? I kind of wanted you to have fluency in this, or I wanted you to have this understanding, and it's missing. So without putting any blame on previous teachers, because that's always a temptation, but teaching is hard, we know. What are the things that in the classes you're teaching right now, or classes you've taught recently, understandings that you wish your students had, that like you wish they were bringing in so they'd be really prepared for what you're trying to do with them? If you take like 2-3 minutes to introduce yourself to your neighbor, say where you're from if you don't know each other, and then what you're teaching, and discuss that. Seeing if this is live. Nope. All right. Let's see. Testing. Oh, great.
Oh no, they're not. Let's get use this. A little red button. That's done. I'm ready to teach.
I'm in North Salem, like let's just back wings.
Any favorite games?
I play your pick.
Oh yeah, I like how. Yeah. Right, it's quick. Yeah. Right. Little great then there. Yeah. What do you teach? What grades?
Keep out. I'm gonna call you out on to.
Oh,
That's fine.
are you teaching at a community college or a tier college?
I'm
Okay.
for trying to find out too.
Okay. Yeah. I was getting ready. I think it's college. Okay. They call it college algebra.
I don't.
I feel fancy if you're getting college algebra.
I'm back.
All right. If you could wrap up your conversation I mean, obviously, the person next to you is going to be more interesting to chat with than listen to some guy on the stage. And I'd love to hear if anyone wants to share what those understandings are. Anyone have here? I'll leap down. Try to do my best, Howie. Anybody have anything they wanna share? Understandings that I would love to get 3 volunteers. That's the dream. Yeah, thanks. Yeah.
It's interesting.
Do you want a mic?
Sure. I have a big voice. It's interesting. I teach Algebra 1 in high school, and Randy is a math interventionist, if I got that right, in elementary school. And the list that I gave him, his was the exact same list.
Oh, that's fascinating. What was on the list?
Operations with integers, place value, rounding, multiplication tables. I teach the algebra program for students with disabilities, and factoring is almost impossible because they can't even tell me what multiplies to 6.
Understanding of the unit.
Yeah, what else did we have?
Understanding of the unit. I can grab back. Understanding of the unit.
Right.
Sure. Yeah, that's. Raise your hand if similar themes came up in your conversation. Yeah, that's right. It's like half the room right there. Yeah, I mean, one of the fascinating things about math is there's so many topics to cover, right? The curriculum is so long and the standards are so detailed. It comes down to it, there's like 6 things in math. And all of those variations in the standards, it's like the same deep structural ideas. The educational theorist Jerome Bruner is someone who articulated this very nicely in the 20th century, right? Talks about how basically math is like there's this trunk of the tree. And then we spend all the time looking at the leaves and the branches and like just being fascinated and dazzled by the variety, especially as a student, that's your experience. But like it all grows from the trunk. If you can really wrap your arms around the trunk, you kind of have the tree. Yeah, thanks for sharing that. It's right interesting to have such different ages, the same problems coming up. Anyone else want to share things? Yeah, let me sorry, back there. Yeah, it's interesting to me how much commonality there often is.
We have another Algebra 1 specialist here, and I'm currently the executive director of multi-tiered systems of support. And we talked more about agency. We want children to bring a desire, a curiosity, a willingness to engage in things that they're uncomfortable with. And so I'm going to let my partner add to that.
Yeah, because I'm saying I'm teaching word problems right now, and they lack the ability to like think about them and make them real world. Like they want to be led, and we want them to think.
Yeah, thanks. You raise your hand if that similar thoughts in your conversation. Yeah, no, right. It's interesting because it's not a specific disciplinary or topical, piece of mathematics. But that sense of ownership and agency, I think, very important in any subject, and especially in mathematics. I think it's very easy to feel extremely alienated from the material. Word problems feel like they take place in some very undesirable fantasy land. It's like Lord of the Rings or Harry Potter, but like much less relevant and real. And so why am I invested in these? Why do I care? It becomes this game of like, let me find the numbers and smush them together, and like, okay, I'll multiply those 2 numbers. Right? There's a famous study of the word problem, where you give students the problem. A shepherd has 125 sheep and 5 sheepdogs. How old is the shepherd? And the students go, 25. Not all of them, I should be clear. Some of them say 130. And including the rare 625. Wow, that is like an Old Testament shepherd. That is from the Methuselah line of shepherds. Like if you push them on it, like they'll actually say, like, what? This makes sense. But I guess the point is that like, they sort of know it doesn't, but they don't think math needs to. Math is this game where it's like, I don't know, somebody gives me numbers and I do a thing with numbers. And that's what happens in math class. Any more volunteers? So anyone else want to share? Yeah, up here in the front.
I wish my students knew that the equal sign is a state of being verb, that one side is equal to the other, and not an action verb that this is the answer, because they don't understand that.
Yes, every hands up in the air for the same issue. Yeah, it's one I've thought so much about. Yeah, I call it the ta-da error, where students sort of think like, 7 plus 2 equals ta-da 9. And so this happens again. There's a famous study where if you give students a problem like 2 plus 7 equals blank 3, right? Like we all know what should go there. 2 plus 7 is 9, so blank plus 3 also needs to be 9, so it should be 6. What do you think the students write? They write 9 because 2 plus 7 equals ta-da 9, and then like later we add 3 or something. So they're, and that's one I've wrestled with a lot. to some extent, I think there's kind of developmental stages in going through math. And so when I see a student, I think early in my career, this would like set off alarm bells. It's like, oh no, someone hasn't taught them how equations work. This is a crisis. Now I view it as like, we have one way of approaching this. Probably worked for a lot of the math they've done in the past. It's not going to work anymore. This futon is going to break. So it's time to build a new one, time to build something new. And so, right, one of the problems with every metaphor has its issues. One of the problems with my futon metaphor is it kind of suggests the futon is irreparably broken. But I guess the nice thing about it is you can get a new futon. Futons are actually cheaper than you might think. Very bulky, but like, IKEA sells them for $100. So, what I've got for the rest of the slides is two kind of case studies in building new futons, trying to replace that broken thing. It's not. I hesitate again. I think it's not totally fair to call a student's understanding broken, right? Like students have these beautiful, complex, interesting worldviews. But I think often the students will self-report that they feel broken, right? They feel like something has gone wrong in their math education, and now it has come to an end. So this is, if I were talking about a room of students, I don't think I would use this metaphor, this language of the broken futon. But kind of behind the scenes among teachers, I think we can understand students feel something has gone wrong. We need to help them make it go right. So two case studies. The first one, this is one that I think most students wouldn't view as a hard part of math. And in fact, wouldn't view as something that they have any issues with at all. And yet when I've taught middle school and high school, when I've taught calculus in particular, there's a lot of calculus problems that basically boil down to, can you turn the machinery of the calculus symbols? And do you have a nuanced, flexible understanding of perimeter and area? And I've seen students stumble over either of those. Sometimes they have trouble turning the crank of taking the derivatives and setting equal to 0 and all that. And sometimes they can do that part, but they don't have intuitions about how area and perimeter should work. So I'm going to give you a few problems to think about. These will be actual, some math for you guys on a Saturday morning. You get to get a taste of your own medicine, feel what it's like to have someone throw math at you through its period when the coffee's barely kicking in. So this is what instruction looks like for perimeter and area. It's like, here's a bunch of rectangles, find their perimeters, find their areas. It's fine. Like, we need some practice. It's not the most inspiring. And you can imagine like the experience of doing a page of these. You almost just like fall into this rhythm where you're sort of just like you're doing the routine and it's the same thing over and over. This is why distributed practice is often more effective than a relentless worksheet of all the same kind of problem. But it can leave some gaps. So what I want to do is focus more, especially early in instruction, on like, what is the essence of these things? Not how do we calculate it, but like, what are these for? What are these about? I'm going to do a quick poll here because I have thoughts on this, but I don't want to. Well, I don't want to come down too hard on the people who are wrong. So hands for edge brownies. Raise your hand if you prefer edge brownies. Raise your hand if you prefer center brownies. Okay, thank you. It's always difficult to be sharing a room with so many just edge people who people who look at the most precious thing in the world, right, the greatest object mankind has created, and they're like, yeah, but I wish it were burnt. I wish it were a little. I wish it were tougher. I want my teeth to work harder. Anyway, but that's fine. I applaud your conviction and your toughness. Anyway, so this is a debate about sweets, which is usually what I like to be thinking about. But it's also a question of kind of a visceral question of perimeter and area, right? So if I go, there we go. You can imagine a problem. I talked about this in my first book. You can imagine a situation where you've got a choice between making one giant batch of brownies in one big pan and 4 little batches, right? So say you're going to get the same total amount of brownies, same amount of batter. It's just which one you want to do. Raise your hand if you'd like to make them in one big pan. Raise your hand if you'd like to make them in 4 little pans. Okay, and this, I can't check. If we had photographs, we would check. Presumably this is the same. Raise your hand if you are an edge person and you want to make it in one big pan. Okay, right. All right, fair enough. Yeah, so there might be different effects here. But yeah, like the fundamental difference here is that you're going to get the same amount of brownies, but one of these is edge heavy and one of these is center heavy, right? So doing 4 little pans gives you, I've got the numbers here, 16 corner brownies. Raise your hand if you like corner brownies. You're really, oh my goodness. Oh my goodness. Because, part of life is just learning to share space with those with whom we disagree. And that's fine. And honestly, there's a symbiosis here because like you can have the corner brownies. That's fine. I don't need them. So 16 corners, right? Because you've got 4 corners in each of the pans, whereas the big one only has 4 corners. You can count the edges. This is like an exercise that right you can do in upper elementary. Right, how many edge pieces, and you get more edges. And then of course the big difference here is the centers. There's only 16 centerpieces on the left, just 4 per pan, and on the right you've got 36 centerpieces, right? A 6x6 thing in the middle of centers. So I think the choice is clear, although I leave that ambiguous. For you, the choice is clear, and maybe it's the wrong choice is clear. Okay, so that's kind of like a visceral, physical sense of what perimeter and area are about. There's also but this isn't much of a student task. Yeah, they can debate brownies a little bit, but I like giving students something to chew on, to wrestle with. Oh, and by the way, something to chew on and wrestle with. This is one thing I will say is a structural unfairness in the world is you edge folks, you wonderful people who I admire. You can do this, right? Like this is available to you. You can create a thing entirely of edge brownies, right? Where like the perimeter is effectively the entire shape. You can go arbitrarily squiggly. In fact, if you wanted it to be even edgier than this, you could have twice as many zigzags, right? You'd be getting like weirdly skinny brownie pieces, but they'd be very overcooked, which is what you folks love. For the center people, you can't do it, right? There's just limits on how much center you can have to a shape. It needs to have a perimeter. And so area and perimeter are fundamentally different in that way. You can make an arbitrarily squiggly, windy shape with as long a perimeter as you want, right? This leads down the road to fractals, where you can have infinite length. If you edge brownie people, that's the dream, right? Fractal brownie, where it's like edge upon edge upon edge, all within a finite space. Area people, we just like center people, we can't do that. What we want is area, and there's a limit, right? Within a certain zone, you can do like the best you can do is a circular pan of brownies. That'll minimize the perimeter for a given amount of batter. Square is better than other rectangles, but there's just limits on how well you can do. So the way I like to kind of instantiate this for students, and I'll have you guys think a little bit about the puzzles here. So I like to give them a rectangle, say 7x4, and sometimes I frame this problem differently. And then I say, okay, make a rectangle with a bigger area and a bigger perimeter. This one's easy because just that's a bigger rectangle. And then another one, make an area with a smaller rectangle and a smaller perimeter. Again, this one's easy. Although you'd be surprised, students don't always find it easy because they go, whoa, what? How big? Like, I don't know. This is actually an unambiguous question, right? The language is perfectly clear, but students are very used to worksheets that look more like that first slide, where it's right. Here's a 5x11 rectangle. Here's a 10x6 rectangle. So given those choice variables, which is much closer to how you're going to use math out there in the world, they can freeze a little bit. And I'd like them to do that freezing as early as possible in their math education, so they can then get over it and learn how to just handle even that small amount of freedom. But really, the questions that I'm looking for are these last two. What about a smaller area and a bigger perimeter? And a bigger area and a smaller perimeter? Take a minute with the person next to you, just come up with rectangles. My guess is we will not all come up with the same rectangles here, but come up with 2 rectangles that fit that description. So number 3, right, a smaller area than that one, so smaller than 28, but a bigger perimeter. And then finally a bigger area, but a smaller perimeter.
Oh, the smaller room.
And it is. How's it going? Hey, how you doing?
Good.
Rectangles here?
I don't. I'm thinking. I'm listening to them actually. Listening to Cole and Aaron. I bet they do. So
But they kind of pretty
you totally.
good, right?
Start writing it down.
Got your okay now.
Yeah. Sorry.
1 by 25. Yeah, that's your yeah. And what's the? Do you have a bigger area, smaller perimeter? Oh no, we were just working on that.
Just change running the size. So starting by
It's like square is optimal, right? But like 28 is not a perfect.
Now we like bigger areas.
So I mean, it's close to me.
That's when I was whenever right with the two screens. I'm like, where?
Yeah, I was that one. She's looking at that one. So we
Yeah, it's
each other. Yeah.
Okay, what was your smaller area here?
What did I say? 11 by 2.
5.4 to 5 point
Bigger perimeter.
next to a bigger
Yeah.
area. It's going to be a smaller perimeter. It's going to be less than 1.
Okay,
Good.
That's good too. Sorry. Okay, 6 by 6.
Really liked your slide that had the picture of brownies. I like the one that had this, but I see one's like 2 to 4 that.
Oh, sure. The
Hands.
hands like 4 hands.
Something like that. Yeah.
Yeah.
And then the one that is like picture. Not drawing, but actually.
Oh yes, yes. Not
Yeah, no, it's all good. It's all good. Oh, it's wonderful. I'm really enjoying it. Thank you.
Yeah. We can't get the last one. Let's get tough. So,
nothing with any.
practice on it. Yeah, we were playing, so it's 5 by 6 if you see area. Sorry, yeah, same thing. Same grade.
So let's just take it down enough.
So
Just one.
Yeah, so so it's a 5 by 6, so you 5 by just under 6. Then you'll shrink the room. And the area will go down a little bit, but you still have some space.
Yeah. Anyone finding the last one weirdly hard? Yeah. Okay. Great. No, I love it. Love it. Which, as much as anything, what I kind of like about questions like this is, like we all know perimeter and area, but weirdly, there's depths here that are worth exploring, right? So, in a room full of math teachers, you can have a bunch of people stumped on like I'm trying to make a rectangle with a bigger, what is it, bigger area, smaller perimeter, and suddenly it's like it's hard. It's a tough question. It's just a tough question for a third grader. It's like a tough question for a grown up who knows math. Which I think is cool. That like there are puzzles to be found in this territory that are tricky. And interestingly, it's often they're trickier because they don't have a single solution. Right? We all know the experience of like Sudoku is a classic experience of this. You just like your eyes are scanning very quickly for information, and you know there's a solution, and you're kind of making these leaps of like, okay, that needs to go there, that needs to go there. And then when it's freer, there's like, I mean, there are in theory infinitely many such rectangles, but actually it's harder to tap into that infinity than it is to find if there were just one such rectangle. Might be easier to find. Anyone want to share? Just shout out a solution for the third one. Anybody got a good one? Yeah. 1 by 25. Okay. Any others? 9 by 3. Nice. Yeah. Yeah. 9 by 3. Others? Yeah. 20 by a half. Sure. Yeah. Nice. Others? Notice what do those rectangles have in common? Yeah, 9 by 3 is like almost, it's like 3 times longer than it is wide. 20 by a half, right? What was the middle one? It was 1 by 25. So 1 by 25, very long, skinny. And 20 by a half is like, it's like a little flat piece of paper. I don't know. Very weird looking rectangle. It's not usually how we draw rectangles. You can, right? There are rectangles like that. So for bigger area, smaller perimeter, what are we going to need to do to this rectangle? Yeah. 10 by, oh, sure, yeah, 10 by 3. Yes, yeah, for, let's see. 10 by 3, I think, does that fall in category 1, maybe? 10 by 3, bigger area. Yeah, and a slightly bigger perimeter, I think, than this one. Yeah, Howie?
5 by 4 by 5 by 4.
Was that 5.4? 5.4, yeah, let's see. So 5.4, of course, Howie's going to make me multiply 5.4 by 5.4. 25 and something. 25 and a bit. But it's actually not too bad because 0.4 times 5 is 2. So we get to add 4 onto the 25. So it's 29 and a bit, 29.16. And that's bigger than 28. and then 5.4, right? The 5.4 and the 5.4 will add up to 10.8, which is just a little less than 11. So yes, that has a smaller perimeter and a slightly bigger area. Cool. So that one works. Anybody else get a solution for the second one? Yeah. 5.3 by 5.3. Love it. Yeah, I like multiply 5.3 by 5.3. It's slightly larger than 28. I'm assuming. Yeah. Oh, sure. Yeah. So yes, that one actually I like, because even though I don't know what radical 29 is off the top of my head, I know it's bigger than 5. It's smaller than 6. I guess perimeter there is a little tricky to verify. But yeah, right. That's radical 29. Root 29 times root 29 clearly has area 29, so it's a little bit bigger. What do all those solutions have in common? They're all squares, which is kind of what you need if you're trying to get a big area and a little perimeter. Squares are the best rectangles for that. So you can do, it doesn't have to be a square, you can do sort of squarish rectangles. 5.4 by 5.6, sorry, 5.4 by 5.5, let's say, would also work. So there's other options, but there's not much territory there. Whereas for number 3, right, let's see, do I have, oops, oh no, there we go, okay. Thought I was going to turn on a little red light that was going to be my pointer, and instead I just extinguished the whole thing. For the third one, there's you can go as far as you want, right? You can make an arbitrarily long and skinny rectangle, right? Another option would be a rectangle that's 1,000 by 1,000, like 0.001. That only has area 1, but it's got a very large perimeter. So let's see. I can turn up the heat on this one, but anyway. We can do this. This is even tougher in some ways than number 3, right? At least double the perimeter and at most half the area. Oh, actually, I just gave that one away because my 1,000 by, okay, we'll skip that one as with partners. If you want to make it really tough, then you can make it so that you, oops, skip past that. I didn't write this down. If you need integer solutions, then it gets tricky. So, and often when I give this problem to students, I'll say, rather than giving them the 4 by 7, I'll say, just give me 2 rectangles, one that has double the perimeter, at least double the perimeter of the other, but the second one has at least double the area. That is a little paralyzing if you haven't already done a few problems that kind of build up to it. I wouldn't start the class with that. But there's like rich, hard stuff here to work on. And interestingly, this works fine whether you're talking to 6th graders or like high schoolers, even high school teachers can spend a little while wrestling with these problems. Anyways, it's one case study of how to kind of find depth, how to make something new in what seems like familiar material. Another one, mean versus median. A lot of the teaching I've done lately has been intro statistics. And before you get to null hypothesis testing and constructing the normal distribution central limit theorem, like all of that is built on having a good understanding of mean and median, which again is something the students have seen pretty early in their math education. But there's depths here. There's intuitions that they need to build that are tricky and subtle. So again, standard practice kind of looks like this. I think I Googled mean median worksheet. One of the more boring Google searches I've ever done. And like, this is fine. It's fine. You know, you can practice it this way. But what this is going to be missing, because these are decontextualized examples, right? They're like, this isn't the mean of some data set that has some meaning for us. It's just some numbers. And so what you miss is why do we care? And what's being communicated? So mean and median, I like to emphasize to students, these are summaries. And every summary leaves something out. So here's an example I like to show. We've got a little conversation. This is back in my phase when I didn't know how to draw necks on stick figures. I spent several years drawing their necks way, way too long. So please learn from my mistakes if you decide to draw stick figures. The necks don't need to be this long. So the slightly shorter but still very long necked stick figure says, but it's really short legs too. Sorry, I'm going to dwell on my own shortcomings in my drawings. What would my starting salary be? And the other one says, I'll put it this way, our average, let's say that means our mean starting salary is $80,000. Real quick with your neighbor, what could be going wrong here? Right. Does anyone want to venture a guess? Now we don't know what this taller, confident-looking stick figure has up its sleeve, but any hunches as to what may go awry in this job offer scenario? Yeah.
Three people in the company, one makes 158,000, the other two make 1,000.
Yeah, this would.
3 people, 178,000, and 1,000 and 1,000.
Yeah, that sounds. Yes, sure. Yeah. Let's see. 80. Yeah, it might be right. You might need slightly more for that wealthy person, but yeah, same principle. Yeah, and indeed, right. This one, with $1,000 salary would probably run afoul of labor laws. I think New York has a robust system of labor protections. But yeah, same basic idea. That's exactly the principle. So what I'm picturing here is, maybe what's this, 8 coworkers. Right. The average comes out to 80,000. But that doesn't mean that the typical person is making 80,000, right? Because an average, as we know, an average is computed. And in fact, when I teach intro stats, students know how to compute an average. What they don't have, though, actually is a flexible understanding of what an average does or what an average cares about. An average cares about the size of the data set and it cares about the total. And that's very clear from when you see it calculated. You add up all the data and you divide by how many points there are. But you need to see some actual data where it's like, oh yeah, the total is all that matters. So that extra $400,000, it doesn't matter to the average whether it's distributed evenly across the 8 employees or whether it all goes to one special person. So the median must be better, right? Like, well, no, the median is different. The median has different blind spots. So here's an example, and this, by the way, don't invest with a fund that talks about their median return rate. That is already not good practice in the financial sector. But again, right, why should I invest with you? Well, not to brag, my fund has a median gain of 8% per year. The reality could be something like that. I think that we have one more good year, right, positive year than bad year. But this is a fund that not only, especially the way percentage growth works, this is a fund that would have lost virtually all of your money by the end of this time. Like, forget it's a little bit behind, like your money is gone at this point. And then, of course, so mode must be better. Like, no, nobody thinks the mode is better. People hate the mode. Mode does have uses, right? Like, the mode is valuable. Particularly when you have categorical data, like mode is kind of your best option. This one I like is that we have this little manipulative student, right? My modal category is 70, 80%. One of the dangers with modes, of course, is you get to design the categories. So let's say we could have a data set like that. The most common value is the 70s, but not going to be a great best average based on those scores. Right. So what are the problems? What are the puzzles that get students thinking about this kind of stuff? I like to work with pirates because, do I like to work with pirates? I've never tried it. I might like to work with pirates. I like to talk about pirates. So here's a question again. I'll give to you and your neighbor. Divide 9 coins, just 9 coins, among 3 pirates, so that the mean and the median are the same, so that the mean is less than the median, and so that the mean is greater than the median. And then this is the key point. That's similar to the rectangle question, right? Construct an example. But this one, I want then students to talk about how will the pirates respond to this, right? In each case, how will the 3 pirates feel about the arrangement? Which one is likely to be a stable arrangement, and which one might lead to a mutiny? I'm going to take a minute real quick and talk about those 3 scenarios with your neighbors. See if you can come up with 9 might be enough. You don't need to pull out your tablet, but if you want pencil and paper, that's also useful.
Yeah. True.
How's it going? Is there any occasion for the kilts? Oh, I like enough. That's neat. Let's go. Jamar. Well, where you come from? SUNY Pitt. Okay, Plattsburgh. Okay, Plattsburgh. Cool. Okay. St. Paul, yeah. Yeah, Minnesota. Oh, cool. Nice. Yeah, no, I love it. You get to go visit up there much, or? Yeah.
Having to refuse 3 times or something.
Yeah, no, it's beautiful in the summer, bitter in the winter, but that's right. No, that's fair. That's fair. Yeah, no. It's beautiful in the winter, just cold.
There's such things as bad weather. Just horrible.
That's a lovely thought. Yeah, I aspire to that world too. I'm not sure. Sometimes I feel like the weather is turning against me. But all right. So I realize it's a Saturday morning. You didn't necessarily come here to calculate means and medians, but thank you for playing along. Um, we've got, let's see, up there we've actually got solutions for 1 and 3. I guess I'd already given you, right? So splitting them equally. Very egalitarian pirate society. I believe there were some such pirate societies. It's slightly unusual, I think. Mean and median are equal, right? They're both 3. By the way, with 9 coins among 3 pirates, one of the important observations which students will have while working on this problem is that you can't control the mean. The mean is not something you have any influence over. The mean is 3. And so it's only by arranging the coins you get to control what the median is. So on the bottom, we have the mean being greater than the median because one pirate is making out like a bandit, like a pirate, you might say, and the other 2 pirates only get a coin each. If we wanted to go the other way, right, and have a higher median, so the second option, then we'd have 2 pirates, maybe getting 4 each, and then just 1 coin for the last pirate. Also, if you just give that pirate nothing, then you've got other options as well. So that's and then another problem along those lines. This one more of a closed problem. In a group of 5 pirates, the richest pirate suddenly finds 1,000 gold coins. And this we do almost a whole day of problems, kind of like this in my stats class. So the pirate finds 1,000 coins, but won't share them. And then how does this affect the mean and the median? So what I like about this is it's really frustrating for students. It foils them completely. You can't just launch right into a problem like this. We need to do a few examples. But they don't know how their gold was distributed before that. In fact, you don't even know how much gold they had before. Maybe they already had 10,000 coins that they were sharing. Maybe they had 15 coins they were sharing. We have no idea. But we actually can answer this question. Because whatever they had, we know what the total grew by. The total grew by 1,000. So if that 1,000 were shared equally, that would be plus 200 per pirate. So the mean doesn't care how things are distributed. The mean only cares about the total and the number of pirates. So the mean just grew by 200. We in fact know exactly how much the mean grew by. And this is sort of an algebraic kind of thinking. This is something that you could prove with algebra. You don't necessarily need to do it through notation, though. This is something intrastat students, we just do this by reasoning it out. And then as for the median, again, we can reason this out. If you sort of imagine those 5 pirates in the line, poorest pirate up to richest pirate, when that richest pirate gains 1,000 coins, nothing happens to the pirate in the middle. The pirate in the middle is just sitting there doing what pirates do. I don't know, enjoying edge brownies. All right, last thought. I've just got a few minutes left before it's 9 o'clock. So I didn't mean to call you all pirates. The best kind of pirates. Something I try to do in my teaching, and once I remind myself to do it, I think it's actually pretty easy, is to dignify the struggle that students are having. So students like Karen, who are working their way through mathematics and finding themselves hitting what feel like ceilings, what feel like impossibilities, feel like they're just stretched beyond their capacity, right? The same way I'd feel if I were like, I'm gonna go out there and run a 4-minute mile. It wouldn't happen. My body wouldn't do it. And so it'd feel like, okay, that's it. This is how students often feel. So how do I help dignify the struggle? Especially what makes it really hard is when they can see the other kid across the room or in the next desk isn't struggling in the same way. Right, so how do I reorient them from that kind of lateral comparison where they're like, how am I compared to other people? And think instead about their relationship with the mathematics itself. So this is a blog post I did ages ago where I just took some kind of typical statements that students might make and then just imagined kind of editing them, going through, taking a pen. So this class makes me feel stupid. I'm so bad at graphing. When I taught trig, this was a very common complaint I don't think my instruction on graphing was the best at the time. But how would I edit that statement? I would say something like, makes me feel not stupid, brilliant. I'm so bad at graphing. Like, no, I'm learning a conceptual framework devised by the greatest philosopher. And to be fair, actually, I did this blog post ages ago. Now it makes me cringe a little to imagine calling Descartes the greatest philosopher of the last millennium. He was like top 10, maybe. But that said, real bright guy. And graphing is importantly from the last millennium. Mathematics is ancient. Graphing is not. Graphing is a weird modern data visualization technique. And it dates to pretty much the same time as calculus, right? Like within a generation and a half, you go from graphing to calculus. So when we're teaching graphing and we're teaching it young, this isn't basic stuff. This is, in fact, pretty baroque modern mathematics. There were people solving cubic equations by hand before anyone had ever drawn a graph in the world. So it's tough stuff. This one, again, very common. I failed the last test. Must be terrible at math. Something I often wrestle with as someone who does give tests is like tests are just tests. So my edit there would be I failed the last test, but I must not overrate the capacity of a highly artificial assessment to measure the full richness and breadth of my abilities. Of course, this is just how students speak. That's exactly their voice. Also, I just don't get how to work with negatives. I've actually been doing some reading lately on negatives and kind of the history, 19th century British history of negatives. And negatives are weird. Negatives are really weird. So my edit here is, I find this generalization of the natural numbers awkward and counterintuitive, putting me in the same place as centuries of mathematicians who just didn't get how to work with negatives. Negatives are really weird. They're like 19th century British mathematicians. Hamilton was one of them, the guy who invented quaternions, saying like, I don't know if this makes sense. One of the correspondents of his was saying, like, I don't know if we should be teaching about negatives at Oxford and Cambridge until we can figure out what's going on. It's basically like, shut this down until we know what's going on with these things. Why is a negative times a negative a positive? Basically, there was no satisfying answer. And we didn't come up with a satisfying answer. We just changed the definition of satisfying to say, well, it continues a pattern. And like for 19th century mathematicians, that wasn't a satisfying answer. But for us, you got to find it satisfying because you're a sixth grader and I'm teaching it to you. So I'm nowhere near as good at math as this one classmate of mine, especially in the second school I taught at, where a lot of really strong mathematicians, they would just get turned off by looking around and be like, well, not as good as that guy. But we can put this in quotation marks and then said David Hilbert, who like literally set the agenda for 20th century mathematics, was sort of one of the most influential mathematicians of his day. And I think it was Herman Minkowski, who's a classmate of his, who was like just better. Everybody thought Herman was better. So David was like, I'm not really a math guy. Herman, he's good at math, but me, nah, not really. And it's just like there's always a better mathematician out there. Everyone can find a better mathematician. So it can't be about being the best. It's got to be about your relationship to the material. Another very common one. Half the time, I have no idea what my teacher is saying to my students. But just say, hey, glass half empty, glass half full. Half the time, I'm getting something out of it. No good at math, just too slow. Raise your hand if you've heard that one from students. Speed, yeah. Oh, right, fewer hands than I might have guessed. Yeah. Maybe the message is getting through to students that like speed is not the highest virtue. Because we say that with our words. We're like, no, it's okay. It's not about speed. And then we give timed assessments and we give everyone the same work. And then whoever finishes first, we go, oh, good job. And it's like, yeah, so we're saying in other ways, and I do this too, like there are other ways our classes say that speed matters. So to edit that one, no good at math. I'm so good at math. I just prefer to go slowly through intellectual achievements that took humanity dozens of centuries the first time around. K through 12 math is a speed run of literally millennia of intellectual progress. There's a lot being compressed in there. There's no reason to think it's all going to click the first day you see it. And then finally, math just doesn't make sense, which I've felt. There are moments in my mathematical education where that seemed true. And for that one, my edit is very simple. Yet, give it time. So I think that's it for me. Thank you so much for listening and playing along.
Thank you. Thanks everybody for coming to the keynote. There's a coffee break outside, and if you need me to sign any of your CTLE, I will be happy to do so.